Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Dr. Chris Bleakley, who is Associate Professor and Head of the School of Computer Science at University College Dublin. Chris leads a research group focused on inventing novel algorithms for analyzing real-world sensor data. His latest book, Poems That Solve Puzzles: The History and Science of Algorithms, tells the story of how algorithms came to revolutionize our modern computerized world. Welcome, Chris.
Thank you for the introduction and invitation, Gill.
Absolutely. Yeah, so I want to talk a little bit about your book, which I guess just came out, right? So, Poems That Solve Puzzles. Very interesting title. Very interesting title. And you say the book is for people who know algorithms are important, but have no idea what they are. And so it will be interesting. The first chapter of the book is entitled Ancient Algorithms. And so perhaps we can start there. If you can give us a context of what you mean by algorithms and sort of a history of how this term came to be well known, not only in computer science but also in any industry you can think of today.
Yeah, sure. So the term algorithm refers to a well-defined sequence of steps that solve an information problem. So an information problem could be something like sorting a list of names into alphabetical order. It could be performing a complex calculation. And the algorithm is, if you like, a method for solving the problem. So if you perform an algorithm manually, you manually perform the steps one after another. And if you follow the steps correctly, the information problem, such as sorting the words, is solved, is completed. Recently, algorithms have become important because they're the methods that computers apply to solve information problems.
Right.
So the step-by-step instructions that we as humans can read can be transformed into instructions that the computer can perform. And the difference is the computers can perform those instructions at very high speeds and complete algorithms in amazingly short times.
Right.
So that's what an algorithm is. In the book, I give the history of algorithms from ancient times to the most recent algorithms and cryptocurrency and artificial intelligence.
So
I think this.
No, so at the very broadest level, Chris, then an algorithm is a set of instructions, and so one could imagine from the inception of humans, we have had algorithms, right? So ancient humans might have used some sort of an algorithm to find a water hole or a safe hunting area. And so it is simply a set of instructions you can follow or repeat with a reasonable probability of getting an answer, right? Getting an expected answer.
Yeah, that's correct. So, as you say, you could imagine hunter-gatherers step by step searching for a water source or something like that.
Yeah.
Um, the earliest documented algorithms that we know of date to around 3,000 to 4,000 years old, um, from ancient Babylon.
Yeah.
So the algorithms have been found amidst the recorded writings of the ancient Babylonian society. They recorded their writings on clay tablets. So the writing was etched as symbols using a reed stylus impressed on wet clay. And the clay was then allowed to dry in the sun. Now, most of the writings are concerned with things like taxation and running of the king's palaces. But a portion of the clay tablets that have been found describe the mathematics of ancient Babylon. And the mathematics of ancient Babylon was quite algorithmically orientated. The writings describe a problem in the way that our own mathematics textbooks describe a problem. An example I provide in the book is calculating the dimensions of a water cistern, given its volume, height, and the differences between its length and width. So they set out the problem and then a series of step-by-step instructions to follow to give you the answer, which is the length and the width of the cistern in this case. And embedded in the writings is an example, a worked example that the reader can follow.
Yeah.
So these are the earliest recorded algorithms. Scholars think that a lot of these are actually from students' notebooks. They were making notes as they learned how to solve these problems.
Yeah.
The reason that these are so well preserved is because they were recorded in clay tablets, which survived, unlike Egyptian papyrus that was much more perishable, and a lot of those writings have been lost. In the ancient Babylonian case, the tablets survived, buried in the buildings in the ruined cities, but archaeologists started to discover those in the 18th and 19th century, and eventually the language of the tablets was deciphered, and these discoveries are being made around the algorithms of ancient Babylon.
So it seems like, so this started 3,000, 4,000 years ago. It seems like we have a natural tendency toward documenting this in some systematic fashion. So like you said, what's the problem? What are the steps you can take? And those steps are in some specific sequence. And if you do that over and over again, you will get exactly the same results at the end of it. And so obviously this has very high practical utility, right? So do we know, one could argue language is sort of an algorithm too, right?
Yeah. So a language is a means for communicating information from one place to the next. So I'm not sure I call language as such an algorithm. It's more a means of communicating. I suppose you could consider the encoding of knowledge into a language as being steps that could be considered repeatable. But I suppose the language itself wouldn't be an algorithm. Yeah.
So these clay tablets, do they have some language in it, or is just some symbolism that we're interpreting?
It's a fully formed language written on the tablets. So the language is Akkadian.
Yeah.
So it comes from the Akkadian Empire. The symbols used are tuned to the marks made by the reed stylus. So it's called cuneiform nowadays, and which means wedge shaped in Latin. So when you press the clay, the stylus into the clay tablet, you get this kind of triangular, long, thin, triangular wedge shape marking. So the symbols reuse these wedge shapes in various patterns. So if you look at a tablet, it's very beautifully arranged. It's very regular. Everything's in kind of a grid. You can see a grid pattern for these symbols. And each symbol then is a slightly different pattern of these wedge shapes. But it's a fully formed language in the sense that the symbols correspond are concatenated to create words, and it's fully formed words and mathematics and numbers and expressions.
Right. Yeah. And so if you move forward in time, in the second chapter, you talk about the ever-expanding circles and more recent times, how mathematics came to really dominate the field then, right?
Yeah, so in the book, I trace the movement of the idea of algorithms out of Babylon into ancient Greece, and the ancient Greek philosophers and mathematicians added their own discoveries. Knowledge was then passed to a number of centers in Europe, primarily the library at Alexandria in northern Egypt, which preserved and extended the knowledge of algorithms and mathematics in general. The survival of a lot of the mathematical ideas and algorithms into modern times was made possible by work conducted in the golden Islamic age by scholars working in the House of Wisdom in Baghdad, particularly Al-Khwarizmi, who wrote a number of key texts on our current decimal number system, on what is now algebra, and the style that he used in the writings was very algorithmic. It's a very algorithmic way of describing the methods, and his books were later translated into Latin and became a conduit for these ideas into the West. In parallel, algorithms were developed in China, and the one area I concentrate in the book is the use of algorithms to calculate pi, which is the ratio between the circumference of a circle and its diameter.
Yeah.
So we know that pi now is a ratio of about 3.1, and it's an irrational number. So you can never write it down exactly. Writing it down requires an infinite number of decimal places to get it accurate.
Yeah.
So this has become a never-ending quest in mathematics to find the most accurate and version of the number pi possible. So in the book, I talk about the algorithms that have been used over the years to estimate the value of pi. And it gives some indication of how mathematics spread and developed over the years. The Babylonians had an estimate of pi that was 25 divided by 8, which is roughly 3.125, which is accurate to two digits.
Yeah.
The Greek philosopher Archimedes improved on that with a famous algorithm that stood the test of time. It was the most accurate algorithm for about 1,000 years. And the same algorithm was adopted in China, and it was actually in China that scholars came up with a very accurate version of pi in the 5th century that was to stand as the most accurate estimate until about the 17th century.
Yeah, and so further forward in time enters the computer, and so what would be considered to be the sort of the first computer, if that word can be defined properly?
Yeah, so the difficulty here, as you say, is in the definition of a computer.
Yeah.
There was attempts by Charles Babbage to build a mechanical computer in England, but those failed due to the imprecise manufacturing of the mechanical components at the time. The first, what I would call, there was a number of computers developed around the same time during World War II. And you really have to look at the details of them to decide whether they're a computer in the modern sense or not. So there's a few elements are required in a computer that distinguish it from an automatic calculator.
Yeah.
So an automatic calculator will perform a sequence of calculations one after another. If you add programmability to that, so the ability to change the list of instructions that the calculator is performing, you move a little bit closer to a computer. So in a computer, you can alter the list of instructions to be performed, and that makes it computer general purpose in that it can do perform a variety of tasks just by changing the instructions. Okay, so you have a machine that can perform automatic calculations. You have a machine that you add programmability to. The last piece then that needs added in is the ability to make decisions. So a true computer is able to inspect the values that it has calculated and decide on different courses of actions depending on those values. So it is able to choose between possible lists of instructions based on calculated values. So you need all of these properties to be defined as a computer. And during World War II, we had the group in Bletchley Park, which is the code breaking center in the UK, with which Alan Turing was famously involved, that developed computers, early computers, to calculate, to make large numbers of calculations to help break the German codes. Their early computers, weren't programmable. They performed the same sequence of operations, one after the other. One of their machines, Colossus, was programmable and was close to a general purpose, what you would nowadays call a computer. It was electronic. Of course, it was huge at the time, the size of a room. But it was electronic, and it was able to process lists of instructions. At the same time as that development was happening, there was Zeus in Germany, who was who was an inventor and developed a series of computers, starting off with his first computer, which he built in his parents' apartment in Berlin. His approach was electromechanical components, and his series, he gradually added more performance to the computers that he designed, and moved from a Z1 computer to a Z4 computer at the end of the war. Now, the thing at the end, he was hampered by Allied bombing and the impact of the war on Berlin in the later stages of the war. And it's unclear how well the Z4 was really working. The Z3 didn't have the full decision-making capability. The Z4 did, but it wasn't really fully working. So really, I think we need to turn to America to look at the first operational computer. You know, there were these prototypes that were close, but I think it was the Eniac developed in the University of Pennsylvania it was the first operational computer, and I think that really became the blueprint for future devices.
Yeah, so to put this in context, Alan Turing, who everybody knows, was born in 1912. So it's amazing how far we have come in just 100 years or so. And so if you use the term a programmable machine that's able to make decisions, clearly that excludes many of the machines of Industrial Revolution. It could even exclude many of the modern machines, obviously calculators, or even some machines that we call computers are not necessarily computers in that sense, right? They don't make any decisions. And so kind of moving forward in time, the University of Pennsylvania, and what is that invention called?
It's the Eniac.
Eniac.
It was developed to calculate ballistic charts for the U.S. Army. So the U.S. Army had a team of mathematicians, primarily female mathematicians, due to the demands for males enlisting in the army. So a team of female mathematicians that were calculating the shell trajectories for artillery pieces, and the shell trajectories are related to the particular artillery piece, the angle at which it's being set, the wind condition, where the target is, the distance to the target, the relative height of the target. So there's a lot of factors in trying to determine what the right angle is for firing your artillery piece. The mathematicians produced list tables that the field officers referred to in selecting their angles for their and the sighting of their artillery pieces. So producing these tables manually was very time consuming, and a team in the University of Pennsylvania, where the mathematicians were doing their calculations, realized that they could speed things up greatly by building an electronic computer to do the calculations. Work was funded by the U.S. Army, and working versions of the Eniac computer were available at the end of the war. They were never used for ballistic calculations during the war, but immediately after the war, they were actually used for calculations for the Manhattan Project, the design of the atomic bomb.
And so there was some mathematical developments as well. So there was a Monte Carlo technique that came to the fore. There were some practical applications, such as attempts to forecast weather and other phenomena that there's a lot of uncertainty in them. And then some of those mathematics, even though it worked at small scale, sort of break down because of chaos and other phenomena. And so mathematics was sort of developing alongside the machine, and then we come to what is now largely called artificial intelligence. We will take a quick break. Go ahead, Chris.
Sorry. Yeah, I was just going to say, I mean, that's true. Yeah. So the advent of the computer meant that algorithms that weren't in any way practical before could now be contemplated. They could be done because thousands, hundreds of thousands of steps could be done in a very short period of time. So the introduction of the computer has led to an explosion in the variety and complexity of algorithms that have been developed. So you touched on the Monte Carlo method, which is the foundation stone for simulations and even modern weather forecasting. It allows the computer to try out a subset of random scenarios, play those out as if they had occurred in the real world, but modeling the phenomena using numbers, and then to bring those samples together as an ensemble and make a kind of a global estimate of what's likely to happen, even in a very complex system.
Right. We'll take a quick break, Chris, and when we come back, we'll talk about a quick introduction to artificial intelligence and its history, and then we go into where we are. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. So Chris, we are talking about your book, Poems That Solve Puzzles. And it is a history of computing algorithms from maybe 4,000 years ago to the status quo and maybe some speculation into the future. And we talked about sort of the early developments in this area. And sometime in the mid 1900s, 1940s, 1950s, this term emerged, right? Artificial intelligence. It's a very confusing term even now. People have, different definitions for it. I tend to believe that we don't really have any artificial intelligence yet. We will talk a little bit about that. Artificial general intelligence is probably the only AI, should be called AI. Everything else is sort of expert systems. People have different opinions around it. But we talked about Alan Turing a little bit. So there was another person who was also an early AI pioneer, right? Christopher Strachey.
Yeah, Christopher Strachey. So at the end of the war, Turing moved to the National Physics Laboratory in London and started to work with a team into building their own computer. Those efforts were frustrated, and Turing left the NPL, spent a year in Cambridge, and then went to Manchester, the University of Manchester. The University of Manchester, seeded by a Bletchley Park alumnus, had developed their own computer and had actually outstripped the NPL efforts.
What is NPL again? Oh,
it's the National Physical Laboratory in London.
Okay.
That Turing had joined, and they attempted to build a computer. Yeah. After Turing left, the NPL produced a computer called the Pilot ACE, which is a simplified version of Turing's design. And it was at that point in time that Christopher Strachey entered the scene. He was a teacher at Harrow College, at Harrow School. And he was a graduate of Cambridge. He heard about computers and was interested in programming them. And he actually requested the National Physical Laboratory, could he come along and do some programming as a hobby?
Yeah.
At the time, very few programmers were available, and they accommodated him. He did some programming in their device, but he heard about the Manchester computer was more advanced. Got in touch with Turing, who he knew from his university days, and got some time working on the Manchester computer. It turned out he was a natural programmer. Even Turing was impressed by his ability to write code. One of the projects that he undertook was to write a program which generated love letters. So what he did was create a program that used templates of love letters. So it would be things like my adjective, noun, verb, structures, grammatical structures would be coded into these templates, and the computer would randomly choose adjectives to slot into the various positions.
Yeah.
So, for example, he wrote a love letter purportedly from the Manchester University computer, which started, "Honey dear, my sympathetic affection beautifully attracts yours affectionate enthusiasm," etc.
Yeah.
So you can see how it constructed new sentences. It was slightly creative in constructing new sentences. So that was probably the first artificial intelligence program, where as you said, the definition of artificial intelligence is fraught with the best definition I think is or the accepted definition is from 1955 from a researcher called John McCarthy. He defined artificial intelligence as a computer program completing a task that would otherwise be called intelligent if a human were so behaving. So here we have a letter being written by a computer. You would say that writing requires intelligence. So hence you would argue that a computer writing a letter is an artificial intelligence. But the way the computer is doing things is completely different. The algorithm is completely different to what's going on in the brain. It's just as if the task were being completed by an intelligent being.
Right.
Strachey went on to work on a drafts program, or checkers in the US, as the board game where you move counters around a black and white checkerboard. He went on to work on that, which was another more advanced form of artificial intelligence, where the computer was trying to play the game of checkers as if it were a human player. So again, trying to write a program that performs a task that we would otherwise say was required intelligence.
So is he the one who came up with the term machine reasoning?
No, it was actually another researcher who also tackled the checker playing problem. It was an American called Arthur Samuel. He was worked for IBM on developing a program that would play checkers, and he actually initially he thought he'd been bested by Strachey. He read about Strachey's work. He'd been working on this problem of playing chess for some years, and he read Strachey's first paper in the topic and felt that he'd been superseded. But then he realized that Strachey's program wasn't a particularly good checkers player, and Strachey proposed and developed new ways to improve his checker player. And this was the first occurrence of machine learning, which is now used very extensively in products from Apple and Google.
Yeah.
But this was the 1950s. This was the mid-50s.
Right.
And what Arthur Samuel's idea was that rather than tell the computer how to play checkers, you would be better to program in the basics and let the computer figure out what the best moves were to make.
So there were...
So his idea of machine...
Yeah, I was just going to ask. So there were initial ideas of what we now call reinforcement learning then?
That's exactly correct. Yeah. The primitive ideas of reinforcement learning were there in the 1950s.
Yeah.
So he had two versions of his program play against each other. The programs identified features on the board, so patterns of checkers that were potentially good or bad. And he used a scoring algorithm to compare different positions. So his scoring algorithm detected these features in the board, gave some scores for the features and totaled them up and came with an overall score for the position. So the computer would choose the move that would lead to the position with the highest score, its highest probability of winning.
Yeah.
Where the machine learning came in is the weights applied to the scores for each position feature were determined by the computer playing against itself.
Right.
And over many iterations, it figured out what the best
ratings
were,
best strategy,
combining the scores.
Yeah.
Yeah, exactly. In effect, it gave it the best strategy. Yeah, exactly.
Yeah, so you see in the book, in 1959, Newell, Shaw, and Simon introduced a new program. So what's the importance of that?
So this was logic theorist, and they used it to generate proofs of logical logical proofs. So a lot of people would be used to algebraic proofs in mathematics using normal numbers. So if you're told that x plus y equals 3 and x equals 2, you maybe be able to work out what y equals. So you can step by step perform a proof to figure out what values are. You can do the same sort of thing with logical statements. So these are true, false values. So they simplified the problem by concentrating on true, false logic equations. And they developed a computer program to generate proofs for logical relationships between logical equations. And the computer generated these by doing a search. It basically tried every possible manipulation of the equation.
Right.
And gradually, using this search, it generated a lot of possible chains of substitutions and transformations. But over time, it was able to, by trying lots of possibilities, it was able to find paths or chains of transformations between a desired starting point and a desired ending point in terms of the equations.
So,
so it was able to do math. It was able to reproduce the mathematical proofs in key text that was produced by well-known mathematicians. So they felt that this was the first occurrence of artificial intelligence. Now, Strachey was before them, but the problem that they were tackling was very difficult. It was producing mathematical proofs, something up until then that only humans could do.
Right. Yeah, so you talked about this before. So you said the first computer program to display the ability to learn was unveiled on public television on Feb 24th, 1956. And that was Arthur Samuel of IBM. And in 1959, Samuel finally published a paper describing his new checkers program. And the title was Some Studies in Machine Learning Using the Game of Checkers. So the jargon that gets used today, much of that has been in play in the 1950s, even with the crudest of computers that were available then. And then there was a lot of hope about this area called artificial intelligence, but it didn't quite pan out the way, right? So people call it now the AI winters. Is that the 60s that we call it?
Yeah, so it was the late 1950s and 1960s.
Yeah.
So these early breakthroughs in computing, I think, led researchers to be over optimistic about what was possible in artificial intelligence. So we had prominent figures like Marvin Minsky, who's head of AI research at MIT, saying in 30 years we'll have machines whose intelligence is comparable to man. So he said that in 1968. So we've missed that target by quite a ways already. Even Turing said by the end of the century we'll have machines that will converse like humans. Why were people so far off the mark? I think some of it was because computers could solve mathematics.
Yeah.
The people involved in the research felt mathematics was the pinnacle, and that more mundane tasks would easily be solved. It turns out that mundane tasks like walking, running, recognizing objects are very difficult.
Right.
And the only reason that they seem easy to humans is that a large portion of our brains are actually given over to processing visual and auditory information. Whereas doing mathematics is not a natural thing for us to do, and from a evolutionary perspective. So I think the researchers at that stage were just taken in by the ability to do mathematics and this assumption that everything else would follow. In the real world, in dealing with real world signals such as images and sounds and speech, there's huge variation. And computers, until very recently, have been very poor at dealing with those levels of variation.
Right. Yeah, as an aside, Chris, toward the back end of that winter, I was in graduate school and was working on what was then, one of the first, we used to call it expert systems, which is probably the right term, I would argue, even now, for education. And the idea there was to get a graduate student to interact with a computer and really the computer responds with ideas. And so this is a design problem in engineering. And the goal was to develop the intuition of the student by interacting with the computer. And so you want to find the optimum design that's a least cost design. A fresh graduate student doesn't have any experience or intuition to do that. So starts in a random point, and the computer gives that person guidance as to which direction to head. And by multiple experiments in sequence, the student gets to the optimum point. And if you play that game many, many times, we found that the student, develops an intuition. So rather than going to the field and making mistakes, they could make mistakes on the computer. And so just like you're describing, again, in engineering, we had great hopes of this type of technologies really making a dent in education and other areas. And not a lot happened, probably because the computing infrastructure wasn't really there to make very practical applications. And so I want to sort of fast forward. You have in the book, you talk about the advent of internet in the 90s, Google in 2000s, and Facebook later. So these are probably areas that people are familiar with. So I want to come to sort of the status quo today. So where are we now in terms of what people think about artificial intelligence?
Yeah, so things have changed radically. So the AI winters, the funding was cut for AI research projects because so many of them failed, and government agencies refused to put in more money.
Yeah.
And a lot of researchers gave up. What's really changed things is in the last 15 years is the amount of compute power is now sufficient to run artificial neural networks. So up until about 15 years ago, artificial neural networks were too small to deal with any real world tasks. When the compute power was sufficient, researchers could start to use large artificial neural networks, and artificial neural networks can really tackle real world problems, complex real world problems.
So
And
artificial
those
neural
discoveries,
network, yeah, so I was just going to say artificial neural network is really an attempt at what we believe how the brain is working in mathematics and on computers. And it was first coined by Belmont Farley and Wesley Clark at MIT, again in mid 1950s. So again, artificial neural network, now largely called deep learning by some of the later companies, has been in play from the 1950s.
yes, the basic concept of an artificial neural network has been around for a long time. This idea that you can very approximately model the behavior of a neuron, a single cell in the brain, using mathematics, and you can simulate that in a computer, has, as you say, been in play since the 1950s.
Yeah.
The two things that were missing in the 50s were, one was an algorithm for training the artificial network to perform a particular task, and that was solved by the introduction of backpropagation in the 1970s and 80s. And then once that was available, the networks were too small. Computer power wasn't good enough. It was really 2005 that computers were good enough to simulate large enough numbers of neurons that we could tackle real world problems. And that's where the term deep learning was coined. The networks were deep enough. In other words, they contained sufficient layers to do really useful tasks. So where we are now is a lot of the research that's been done is applying those deep learning ideas in all sorts of fields. It's not just the speed of the computers, it's the data sets that can be provided. So if you want to train a neural network to recognize objects, you can now use a very large neural network, very deep, lots of layers, 10, 12 layers, tens, maybe hundreds of thousands of neurons in it. And you can give it examples of hundreds of thousands of images of objects. And it can use machine learning to learn what the correct settings are for the neural network so that it can recognize the objects.
The irony there, Chris, is that, in some sense, I want to get your insight into this. So if you provide labeled cases, finding cat against the dog type experiments, if you have a large number of data points, as you say, the computer is able to recognize that over time. But the human doesn't actually require a very large number of data sets to get to the same level of intelligence. So it seems to me that, I would call it rote learning, the rote learning process that is embedded in deep learning networks. Can we really call them intelligence? Compare that to human intelligence based on the definitions that was existing in the 50s?
I think if you take McCarthy's definition, it is artificial intelligence in the sense that you have a computer program performing a task that would otherwise be considered as requiring human intelligence. So it meets that definition. The problem here is that the popular concept of what artificial intelligence is completely wrong.
Yeah.
So the popular concept of AI is a computer behaving in some way like the human brain and doing things like the human brain. The computer is not thinking in the way that a human brain is thinking. I mean, we can say that artificial neural networks are a mathematical abstraction of the human brain at a very high level, but we're, if you like, we're modeling the periphery of the human brain, the very simple structures that are just behind the eyes and just behind the ears, and it's maybe a rough approximation of that. It's not really thinking in a way that we would associate with humans.
Yeah.
So we're using a very mechanistic calculation to perform a task that otherwise would take human intelligence. We're not yet at the point where programs are thinking intelligently in anything like the way that we're thinking.
Yeah, so are we on a path? It seems like there was some sort of a divergence, if I understand this correctly, in the 70s and 80s, back propagation that you mentioned, as some tools arrived to, as you say, create a mathematical abstraction of people incorrectly believe as the way that the brain is working. Now, a lot of things are on that path, it sounds to me. So the large companies can throw a lot of memory and a lot of computing power behind that in an attempt to show practical applications. Um, but it's not at all, like you say, how a brain functions. So this is where I think, the term artificial intelligence, I believe is incorrectly used, and it has two problems with it. One is more investments go into it on the premise that it can get better. And the other is sort of the confusion it's creating in the marketplace about what is meant by artificial intelligence. On the former, Chris, I want to get your view on this. My hypothesis is that we are going down a path that will never get to what we want to get to, which is artificial intelligence. What is your perspective on that?
So there's a couple of major research projects ongoing in the US and the EU that are trying to better understand how the human brain works.
Yeah.
So using the most recent technologies to really analyze the behavior of the brain. And I think that those projects are likely to reveal that the models that we're currently using in the computer are very coarse and very approximate versions of what's really going on. So we may see some transfer of knowledge from how things are working in the biological brain into improved artificial neural networks. But I think a lot of what we as humans associate with intelligence is higher order thinking,
Right.
analyzing, thinking in your head, listening to what you're saying, thinking in your head rather than reacting to things. So
Yeah.
a lot of what I say, a lot of what's being done at the moment is really just peripheral functionality, reacting to things. So there's a big gap there as how do you get to this next level, and it's really not clear what the path is there. Is it refinement or major changes? I think it's probably both. I think refinement of the models for individual neurons, but also radical changes in the structures. The brain, human brain, you'd have to think is a network of networks.
Yeah.
So we're at the moment we're looking at single peripheral networks, like how do all these networks in the brain work with each other to generate this higher level of thinking. That's really not understood at all at this stage. So I think the innovations are going to be in how large networks interact with each other, as opposed to this low level we're at the moment, which is really just using a large-ish network. Now you start putting them together and your compute demands go through the roof. How do you deal with that?
Yeah, I see two symptoms, Chris, that tells me, or that I believe this is the case, that we need to philosophically change the design path. The first symptom is we know humans don't need a lot of data to actually get to an intelligent decision. It doesn't require 60 million labeled cases to learn something. So that's the first symptom. The second symptom is really about creativity, which is creativity is spontaneously emerging. We don't see humans getting creative by rote learning.
Hmm.
So creative people actually don't take much time. If you use time as a proxy for computing power, you could then test that. Do I put a person in a room and give that person 15 years? Does that person create a creative piece of work? I would argue either he or she creates it in 15 seconds, no, or not, right? And these symptoms that we see comparing humans to existing quote unquote artificial intelligence tells me that we might be mathematically on a wrong track. I might be too pessimistic. What do you think?
Yeah, so this is one of the big problems, is the amount of training data that's needed. It's fine for things like handwriting recognition, object recognition, language translation. We can actually use enough compute power to figure out neural networks that can do those jobs. But you're right, humans don't need that many examples. Humans are much better at generalizing. So
Yeah.
we can take a small number of examples and generalize a solution, whereas computers need all of a huge number of examples. They can't generalize as well. So the question then is, how are humans doing the generalization?
Hmm.
We and there's the other side of the generalization is overfitting. So if you
Right.
get too many examples, you can tune to just particular cases, as opposed to the general, identifying the general pattern. And humans
Yeah.
don't seem to do that either. They don't overfit, and they don't need that many examples. So how is that working? The way that this is being used in computers at the moment is to synthetically generate more examples from, so let's say that you take 10,000 images. You can then mix and match them and distort them and change the color patterns and generate another 100,000 images from those. And that's generating a synthetic data set.
Hmm.
Is the human brain doing something like that? Is it generating synthetic data, or is the human brain got a kind of a general problem solver that it allows it to generalize, to take a few? Is something completely different going on? I
Right.
suspect something completely different is going on. I don't think the human brain is putting in the amount of effort. I mean, if you look at the power consumption of the human brain, it's very, very low in comparison to modern supercomputers. So I think the human brain is somehow um, generalizing using some um, capacity, generalization capacity that it can use across a range of problems,
Yeah.
um, and that we haven't figured that out at all in the artificial network community.
Right.
There are
Right.
some interesting paths in generative adversarial networks and things like that, but I think we're still a long ways off figuring that one out.
Yeah. So in conclusion, Chris, if you look forward 5, 10 years, based on the path that we are on, there are more innovations in engineering. Quantum computing is sort of hovering. We don't know how long that's going to take. There are some applications like cryptocurrency and Bitcoin that again requires a lot of computing power. So, assuming the path that we are on is going to be the path that we would continue to pursue, which tells me that more computing, more memory, more sort of brute force applications where do you think we will end up, let's say 5 years, 10 years from now? There was a lot of talk about the singularity just 5 years ago. By 2027. So what are your expectations looking forward 5, 10 years?
Yeah, I think the singularity idea is flawed. The singularity idea is projecting forward compute power, and when does compute power become similar to brain compute power? I think in terms of that metric, we may be close to having raw power comparable to the brain over the next few years. Now, that's somewhat limited by a slowdown in Moore's law. So Moore's law says that the number of transistors per square millimeter in a computer chip doubles every 18 months. And that was true in the 1970s, but has now slowed down. We're now maybe looking at more like 24 months or more. And it becomes increasingly difficult to shrink those transistors. So we're starting to slow down off that curve. So that may push out what's being called the singularity by, 5-10 years or something like that. But it does look like we're reasonably close to matching with compute power. But I think what we're missing completely here is the algorithms. We may be able to do as many base calculations as the human brain in a supercomputer. But if we don't know what the algorithms are, it won't have the same effect.
Yeah.
So I think we're a long ways off figuring out what the algorithms are.
Yeah, it's interesting. As you mentioned, in the 50s and 60s, we would have thought that the constraint really is the hardware. We couldn't have envisioned the type of computing power that we have today that fast. And we were overconfident in software because it is mathematics, it's algorithms, and we are pretty good at doing that. Now, the problem appears to have reversed in the 2000s, which is we continue to seem to do okay with the computing power increase, but the mathematics appears to be plateauing, at least from my perspective. Do you see it that way?
Yeah, well, there's a problem here in that the capacity for writing software. The beauty of artificial neural networks is the basic unit is quite simple, and you just replicate it, the basic unit, tens of thousands of times, and then machine learning, you just give it examples, and it figures out itself how to solve the problem. So you've taken the manual coding out of the loop here. You have a basic unit, you have a training algorithm, you give it lots of examples, it figures out how to solve the problem. You're not trying to solve the problem yourself. But the difficulty comes if that basic unit isn't quite right. If the interconnection of those basic units aren't quite right, you have to go in and re-engineer this basic system. So that's what I mean about if the algorithms aren't right. If the basic architecture and the basic models aren't good enough to give us this artificial general intelligence, then that's all going to have to be re-engineered, and it's likely to be something that requires human ingenuity. We won't be able to let there won't be sufficient compute power to explore this design space fully, just using automated means. So we may well be in this position where the hardware has the capability, but we haven't yet figured out the algorithms that are needed to exploit that hardware so as to give us something approximating artificial general intelligence. So you're right. I agree with what you say. It's the human ingenuity side that's the limiting factor here. The compute resources are vast now. It's about humans trying to figure out how to use those, and it becomes increasingly complex. The more complex a piece of software becomes, the harder it becomes to understand, and the harder it becomes to develop it.
Right.
And particularly when you're talking about hardware that with parallelism, where multiple things are happening at the same time, that's very hard for humans to understand. So I think you're right. The hardware is not the bottleneck anymore. The human programmers and designers are the bottleneck.
Yeah. Excellent. Yeah, this has been great, Chris. Thanks so much for spending time with me.
Thank you very much.
Good luck with.
Thoroughly enjoyed the discussion.
Yeah, thanks so much.
Thanks, Gill. Bye.
Bye. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.